Okay, so Unit 9 starts with a lot of review. So let's briefly review. I'm not going to talk too much into detail about this right now. If you need a refresher, you can go back to where we talked about this before. But we talked about how there are three basic types of chemical bonds. The first type we talked about were ionic bonds, right? And this is where two ions, or two or more ions, they bond together to form a compound. So couple examples of them are when you have a metal and non-metal, so something from the left and middle of the periodic table with something from the right side, so like NaCl, KBr. You can also have polyatomic ions that are in that mix, right? So the ones that you guys all memorized, right? Like nitrate, sulfate, phosphite, all that stuff. Those can also be involved. So basically, if you have a positively charged ion and a negatively charged ion, you make an ionic compound. Okay. The second type of compound that we look at a lot are called covalent or molecular, and this is formed when electrons are shared. We're going to learn how to draw these this unit, but this is most commonly between two nonmetals or multiple nonmetals. Okay, and then the last one are metallic bonds, where electrons can move freely through the metal. This doesn't come up very much. If you need a refresher on this, you can look back at Unit 1 where it talks about like alloys and things like that. But that's pretty much metallic. So this unit is mostly going to focus on ionic and covalent bonds. So just make sure you're aware of the different. Ionic bonds is when there are two ions, two or more, sorry. And then covalent is where electrons are shared. But we'll get more in detail about that. All right, so a big skill in this unit is using Lewis structures. Okay, so let me give you guys about 2 minutes. See if you can draw the Lewis structures for sulfur, sulfur's MCI, and argon. Okay, so go ahead and try 9.1. I'll give you guys about 2 minutes. You'll probably need your periodic table, so take a look at that. But we'll go over it in a second. Okay, so for this, we're going to need your periodic table. So let's pull out the periodic table. We're going to start with sulfur. And Lewis structures are very easy. You're just drawing the valence electrons. Just count the boxes in the row till you get to that element. So sulfur is box number 1, 2, 3, 4, 5, and 6. So we're going to do sulfur, and you're going to draw 6 dots around sulfur. So that's the Lewis structure. Okay. All right, sulfur's most common ion. If you remember in this column, everybody's -2. So sulfur is 2-. So the 2- tells you got 2 more electrons than regular sulfur. So we have the 6, and then we add 2, and we get the 8. So we get 8 like that. Okay. And then the last one, argon. Same thing, just count the dots. So sulfur was 6, chlorine is 7, argon is 8. So we got 8. Okay, so that's the Lewis structures. Okay, so just a quick thing. Sorry about that. Okay, so we're going to be talking about something called an octet rule. So make sure you guys jot that down. Octet rule. Okay, now octet rule is very simple. The word octet just means 8. So it's the rule of 8. Basically what this is telling us is that elements, they want to either gain or lose electrons until they get 8 valence electrons. So for example, let's look at the sulfur we just talked about, right? Regular sulfur has 6 valence electrons, right? So let me write 6 valence electrons. But what does sulfur want to do? It wants to gain 2 electrons, right? So it becomes S2- in order to have 8. Okay, some other examples of cations that lose the electron. So for example, regular Na is 1 valence electron, right? But it loses 1 valence electron in order to become Na+, so that way it has a complete valence shell. So we talked about how in the previous unit, elements want to have stable, complete valence shells, right? And this is what we call the octet rule. So basically, elements want to have stable shells, so most elements want to get to 8 valence electrons, okay? There are a couple exceptions to this. The most common that we see is helium, because helium is 2, right? Hydrogen wants to become H+, and hydrogen basically wants no valence electrons. But we'll talk a little bit more about these exceptions later, but just keep that in mind, that it's not like an all-encompassing rule. It's just that most elements want to get to 8 by doing this, okay? Okay, so we're going to start by talking about the easier of the two bonds to work with. We're going to be looking at ionic bonds. And what we're going to do now is we're going to be looking at how ionic bonds are formed using the Lewis structure. So before we start, let me give you guys let's take about 2 minutes again. We're going to do 2 and 3. I want you to draw the Lewis structures of Li and Br. Draw them kind of next to each other. Leave a little bit of space because we're going to be working with those. But take a second to draw Li and Br. Alright guys, so let's go over the Lewis structure. So I'm not going to look at the periodic table, but you can refer back to it if you want. If you take a look at Li is the first box in its row, so it's going to be 1 valence electron. If you look at Br, I know that Br is in the 4th row with all the transition metals in the middle, but you skip those, so Br should have 7 valence electrons. Okay, and if you oriented the valence electrons a little bit differently than me, so for example, if you had like this dot right here, or you switch the 2 and the 1 right there, that's totally fine, as long as you got the correct amount around it, okay? Any questions on Li and Br? Chillin'? Okay. Let's do Ca and O real quick. Ca is going to be 2 valence electrons, second box in its row, and then O is going to be 6 valence electrons. Okay. So I'll make a little note. Li is 1. Br is 7, Ca is 2, and O is 6. Alright, everybody good? Okay, so what we're going to do now is we're going to see how these two elements want to become their ionic compound. So if you look at Li, what is Li's most common ion? +1. Yeah, Li is +1. Okay, now, if it's +1, that means it wants to do what? It wants to lose 1 electron. Okay, let's look at Br. What is Br's most common ion? Not +1, -1, which means it wants to gain 1 electron. And you guys can kind of see where this is going, right? So basically, Li wants to dump off its electron, Br wants to gain 1. So Li is going to give its electron to Br. If it does that, it becomes Li plus, and Br becomes minus. And then it's plus and minus, and they're going to be like, oh, that element's kind of cute. And they're going to get really, really close because they're attracted, and they're going to combine, and they're going to become LiBr, and they get married. Okay? All right. Make sense? Okay? Let's look at Ca and O. If you look at Ca, what is Ca's most common ion? 2+, which means it wants to lose 2 electrons. If you look at O, its most common ion is 2-. That means it wants to gain 2 electrons. Okay, and you guys get the point here as well. Ca is going to give both its electrons to O. It's going to become 2+. O becomes 2-. They get close and attracted, and they become cow. Alright, so we're going to talk real quick about some of the physical properties of ionic compounds. You guys do not need to memorize this. I'm just going over it just so you're aware. Ionic compounds are very brittle. They have high melting points. They have a crystal structure, so they form like crystals. So think of like salt. Salt is like the most common ionic compound. If you look at salt, salt's pretty brittle. It breaks apart really easily. Super hard to melt salt. If you've tried it on your stove, like you can heat up your stove like as much as you want. It's not going to melt the salt. They form crystal structures. They also break along very smooth surfaces. And they have a very rigid, well-defined 3D arrangement. And this is the one that's most important to remember. And this is actually because of the chemical properties. So I have a picture of NaCl right here. The purple circles are Na, and Cl is the green ones. Now, if you guys remember, the Na and the Cl are attracted to each other, right? And so because they want to be next to the ion that they have the opposite charge of, they make these nice crystal, like really a well-arranged structure. So for example, an Na is going to be want to be next to a Cl. Cl only wants to be next to Na. Okay, and then the NAs want to be next to Cl, and you guys kind of see the picture, right? They want to only be next to the opposite charged ion. So they make these nice three-dimensional structures like this. So that's the thing to keep in mind, because this gets into a, what is it? It gets to a chemical property. So this actually causes these ionic compounds to be very stable, and it increases something called their lattice energy. So write that down, lattice energy. Okay. So this lattice energy, this 3D arrangement, is the reason why salts are pretty hard to melt, and it's because they have a high lattice energy. Okay. And lattice energy, the definition is the amount of energy it takes to turn 1 mole of the ionic compound, a solid ionic compound, into a gas. So lattice energy is the energy required to turn 1 mole of the solid ionic compound to gas ions. And this energy is very high because of the attraction between the positive and negative ions. Alright, so if we take a look right here, it kind of shows an example of what lattice energy is. If you take a look, you have a solid ionic compound, right? NaCl, it's a solid, and it's turning into Na plus gas and Cl minus gas. So it's always going to have the same format for the equation. It's turning 1 mole of solid into the gaseous ions, and then you get a delta H, so the energy required to do this. Okay, this is called the lattice energy, the energy required to break up an ionic compound into its gases. Okay, it's going to require a lot of energy. If you look, it's a lot higher than the energies that we've been looking at for our enthalpy stuff. And the reason why these lattice energies are so big, it's because of the bonds between the ions. The bonds between the ions are very strong, and that's what causes things like salt to have high melting point. That's why they're very hard and they're very brittle. Okay. So we're going to take a look at a couple examples. So if you take a look at this chart right here, you'll see the lattice energy for different ionic compounds. So you guys don't need to memorize this. Just be aware of what lattice energy is and that it applies to ionic compounds. Okay. All right. Now, there is a little bit of math that we need to do. This is actually going to be a bit more very easy math, but I want you guys to write this equation down right here, the E-elec, and then we'll talk a little bit more about this equation once you write it down. I'll break it down for you, but copy down this equation, and then we're going to annotate it a little bit. All right, so this equation basically tells us about lattice energy. So this E-elec right here, this is lattice energy. Okay, so this is the lattice energy. This is the energy required to break the lattice, to break the ionic compound into its ions. Okay. The K, it's going to be a constant. We're not going to get into the actual math of it, so don't worry. It's going to be a constant, so it'll always just be K. Q is going to be charge of your first ion. So I'll call it charge 1. So whatever charge one of your ions has, this is going to be the value there. Q2 is the charge of the other ion. So this is charge number 2. Okay, and then D is going to be your distance. Okay, the lattice energy is dependent on a couple things. It's dependent on the charges that the elements have, but also how far the ions are from one another. Okay, so greater distance is going to be less lattice energy, and so on and so forth. Okay, so let's take a look at 9.4, and then we're going to try it in a problem. I'll show you how to do it with MgF2, and I'll have you guys do it with the others. But this problem is basically asking us, out of these 3 ionic compounds, which one has the greatest lattice energy? Okay, so let's do MgF2. So for MgF2, we're going to plug in our values. So E is going to equal K, and then let's do Q1 for the cation. If you look at MgF2, what is the charge on Mg? 2. It's positive 2. Okay, because Mg is plus 2. And then what's the charge on F? -1. I know there's 2 of them, but we're just going to be looking at one of the charges. So -1. Okay, divided by distance.
Why do we just look at one of the charges?
Because when MgF2 is formed, that's a good question actually. It's going to look like this. So F is -1, Mg is +2, -1. Lattice energy is breaking these apart. You're looking at how much energy it takes to break apart one of these connections. Yeah, not both of them at the same time. All right, so if we solve this out, the math is pretty easy. It's just -2k over d. Okay. Distance isn't going to matter too much, so we can just leave it as d. And that's going to be our value for the lattice energy. Okay, and here we're not looking for the exact number, so we don't have to solve it out with k and the distance. All we're doing is comparing it with the other ions, right? So I want you to do the same thing for the other 2 ionic compounds we're looking at, CaF2 and ZrO2, and then I want you to see if you can determine which one has the greatest lattice energy. So go ahead, try that out, and then we'll go over it together. All right, so for CaF2, you should remember Ca, what's the charge on that? 2 plus. What about F? -1. So it's the exact same equation as this. So E-elect will equal K, cation is +2, anion is -1 over D. That's going to give you -2kD. Okay. All right, and then the last one, you got ZrO2. Zr, you do not know the charge off the bat because it's a transition metal. But you do know O. What's the charge on O?
That's -2.
-2. And if there's 2 of them balancing out the Zr, what does Zr have to be? 4, exactly. And then so if you plug it in, obviously you can already tell what the answer is going to be. K, -4 times, +4. Ugh. +4, -2 over D. That's going to give you -8k over D. Okay, so if you guys take a look right here, we got -2, -2, -8, pretty much. And I know that the there's a negative sign, but I want you guys to make a note right here. Whenever it comes to electricity or energy, the negative sign means attraction. Okay, so when it comes to electricity, when it comes to attraction, repulsion, negative always means attraction. The reason why it's because it's a lower energy state. And so it's going to be negative is attraction. That means that this right here is going to have the greatest lattice energy. Okay, that's the greatest attraction.
So if it was positive, it would be less.
Yeah, positive will be repulsion, which makes sense, right? Because if you look at the equation, let's say I had like Na plus and Ca2 plus. If you plug it into the equation, it'll be E-elect is equal to K plus 1 times +2. That'll give you a positive number, right? And we know that same charges repel, and so it'll give you a positive answer. So positive means repulsion. Yeah.
Like the CR, like when you put like +4, stopping up and like a negative.
Like why is ZR +4 instead of -4?
I know why it's like 4, like it's positive.
I'm confused. Like what makes it positive?
Like how do you know if you're using a positive or negative?
Oh, yeah. I mean, if you have an ionic compound, you have to have a positive and negative. Yeah, yeah. If it asks you to compare 2 negatives, then you would get a positive number, so you know they repel. Yeah. So it'll have a low, extremely low lattice energy, no lattice energy, because they just want to push each other away. Yeah. Great question. Yeah. So you can use this for like charges as well. Okay. We are gonna skip 9.5 because that's pretty simple. Okay, and now we're going to get into the, I guess, the meat of this unit. Okay, covalent bonding. Okay, covalent bonding is between nonmetals, and the key thing is that they share electrons with each other in order to form an octet. Okay, so instead of giving electrons to one another, what happens in a covalent bond is that elements get really close to each other, and it seems like they have an octet, but they're sharing an electron pair with one another. Okay, so that's the key word. It's about sharing. Alright, so I'm gonna pull up this blank screen right here, and we're gonna just visualize what is going on. So let's start with something easy. Let's start with hydrogen. Okay, so hydrogen has one valence electron, right? Each. Now, what's gonna happen is the hydrogens, if you look at hydrogen, it has only one shell, right? And what's the total number of electrons that can go in that first shell? 2. So there can be 2 max. Okay, so what we're going to do, what's going to happen is when hydrogen turns into H2, what's going to happen is they're going to see each other, and they're going to get really, really close together. Okay, so I'm going to redraw them. You guys don't need to redraw this, but if you redraw them and they get really close to each other like this, okay, the electrons right here, they start getting shared. Because if I cover up this hydrogen, it looks like this hydrogen has 2, right? And if I cover up this hydrogen, it looks like this hydrogen has 2. And so this is pretty much what covalent bonds are. It's where 2 electrons are shared between elements. Okay, they get really, really close, and once they get to a certain distance, the electrons are pretty much within each other's orbits, and it creates a covalent bond where they're shared together. Okay, so that's how a covalent bond works. All right, let's look at one with more of an octet. Let's look at chlorine. If you look at chlorine, how many valence electrons does chlorine have? 7. So we'll do the red chlorine right here, and then we'll do the blue chlorine right here. Now what happens with chlorine, same thing. They both have 7, but if they get close enough to each other, they have this pair in between them where the electrons are shared, right? And so if I cover up the blue chlorine, it looks like the red one has an octet. And if I cover up the red one, it looks like the blue has an octet. So this is how nonmetals form covalent bonds. It's by getting close together so that the electrons pretty much are being shared, but it seems like both of them have an octet. Okay? That's pretty much what a covalent bond is. Okay, electrons are shared. Do you have a question? What do you mean? Yeah, we're going to get to that. When they're the same element, they're the same attraction, but I'll talk about it. So let's talk about things like F and Cl, right? If they're bonding, you look at which one's more electronegative. F is more electronegative. So we're going to talk a little bit more about this, but the electrons tend to be with the F more than the Cl. Yeah, that's actually a big component of this unit, but just wait for me till we get there. Great question, though. Any other questions? Okie dokes. So that's covalent bonds. We're going to do a couple problems together. Okay, we'll do 9-6, and then I'll have you guys try 9-7. So the thing that makes covalent bond drawing a little bit trickier, it's not just between 2 elements. It could be between multiple, and that's probably the ones that you're going to be looking at. So we're going to look at NF3, and then I'm going to show you guys how to draw the structure. Okay, so on your paper, I want you to draw NF3, or write NF3, sorry. Okay, now, the first thing that you're going to do is you're going to count how many valence electrons all of the elements have. Okay, so let's look at N on the periodic table. How many valence electrons does N have? 5. Okay, 5. So if you need a reminder, if you look at N on the periodic table, it's right here. 1, 2, 3, 4, 5. And then F has 6, 7. Okay, so 7, and there's 3 of them. Okay? Everybody good? All right. Now we're going to draw the molecule. But in order to draw the molecule, we need to orient them in the correct way. So there's a couple rules that you need to keep in mind. Okay, so the first rule that you want to keep in mind is that the most electronegative elements, okay, they go on the outside of the molecule. Okay, and this makes sense because if you're in the middle of the molecule, what do you have to do? You have to share. Electronegative ones don't want to share, and so they tend to be on the outside of the molecules that we're drawing. There is an exception to this, and the other element that wants to go on the outside is hydrogen. Hydrogen is pretty much always on the outside, and the reason why is because it's only it's so small, it can only make one connection. So it has to go on the outside, because if you're in the middle, you have to make multiple connections. But hydrogen is super tiny, it goes on the outside. Alright, so what this means is between N and F, which one's going to go on the inside? N is going to go on the inside, and F is going to surround N. So I'm going to draw N, and I'm just going to, again, you could orient this a little bit differently, but we're going to draw F's around the N. Okay, so far so good? Okay, now what we're going to do is we're going to give everybody the valence electrons that they have. So N has 5 valence electrons. So I'm going to draw 5 valence electrons around it. And then F has 7 valence electrons. So let's give each of the F's their 7 valence electrons. Alright, now what we're going to do is we need to connect them together by seeing how they bond. Now if you take a look at each of the F's, let's take a look at this left F right here. This F, how many more electrons does it need? One more. So this F needs 1 more. And what it's going to do is it's going to combine with the N. Okay? How many more electrons does the N need though? 3. So it needs 3 more. So what's going to happen is this F and this N are going to share these 2 electrons with each other. That way this F has this one as well, and this N has this one. And you guys kind of see what this is going to look like, right? And then it's also going to make a connection with this F right here. And then it's going to make this one with the bottom one. Now everybody, if you take a look at it, has 8 valence electrons. Okay. Alright, make sense? Okay, now, before we move on, I'm going to show you guys the proper formatting for this, the way that chemists do it. I did it this way, that way we can kind of visualize how the electrons work. But whenever 2 electrons are shared like this, the way that we draw it is we just draw a line in between them. And this line represents 2 electrons being shared. So that's going to be the other rule that we write. One line, it represents 2 shared. Another word for this is bonding. 2 bonding electrons. Okay, so every time that you see a line between 2 elements, that represents 2 electrons being shared. What's up? Can you tell them to send you to a different class? I can't do it right now. Thanks. Okay, so for NF3, you're going to have these lines right here. You're going to have a line between each of the F's and N. And again, each of these lines, they represent 2 shared electrons. All right, any questions? Okay, I'm going to give you guys one last rule before I have you guys try 9-7 on your own. The last rule, and this is just kind of more of a tip, carbon pretty much is always going to be in the middle. Okay, so if you have a carbon, carbon is going to go in the center of the molecule. Carbon wants to connect with everybody. It's very extroverted. It wants to make as many connections as possible. So just keep that in mind. So I want you guys to try 9-7 with the person next to you. You're going to be drawing CH4. Try to do it the same way that we did with NF3. So try CH4. I'll give you guys about 2-3 minutes to do that, and then we'll go over it together.
You erase it out.
Alright, so let's do CH4. Let me pull up the blank screen again so that we have our rules handy. But let's start with C. How many valence electrons does C have? 4. Okay, and what about hydrogen? They have 1 each, right? So 1, 1, 1, 1. Okay, now if you remember, based on our rules, what element's going to go on the inside?
C.
C. So C goes in the middle, and then the H's are going to surround C. Okay, so it's actually pretty easy. I'm going to draw it out, and I'll draw the lines after. C has 4 valence electrons. Hydrogen has 1. And if you remember, we said hydrogen only wants 2 electrons. So hydrogen connects with C, connects with C, connects with C, connects with D. And that's going to be your structure for CH4. Okay, so if you want to make a note, basically if you have a line next to an element, that means it has 2 electrons being shared. So if you look at carbon, hey guys, if you look at carbon, how many lines are connected to carbon? 4. That means it has 8 electrons in its valence. And if you look at hydrogen, it has 1 line, which means it has 2. And hydrogen wants to have 2 electrons. Okay? And that's how you draw these structures. That's pretty much the gist of it. We're going to do some more practice just to help you guys out. But any questions on the general idea? Okay. All right. I'm going to show you guys now a bit of an easier way to do this that makes it go a bit faster instead of putting the electrons on the elements. So let's we're going to draw. Let me think of something. Let's do NH4 plus. Okay, NH4 plus. Okay, so we can start doing ions now. All right, now the easiest way to do this first is you want to count, same thing as before, you want to count all of the valence electrons. So let's start with N. We just did these, so what's N? 5. What is H? 1, but there's 4 of them, right? So it's going to be a total of 4. And if you look at this plus sign, if something is positively charged, does it mean it gained or lost electrons? It lost. So that means for our total right here, we're going to do minus 1. So in this molecule, we're going to have 5 plus 4 minus 1. That's going to be 8. We're going to have a total of 8 valence electrons. So when we are drawing this picture, we have 8 electrons to work with. Okay? So that's step 1. Any questions on that? Okay. All right. The next thing that we're going to do is we're going to arrange our elements. So if you take a look at this, which element's going to go in the middle? N. So we're going to put N in the middle, and we're going to put the H's around it. Okay, so for H2O, we're going to do the easy method by just counting the valence electrons. So how many valence electrons does H have? 1 each, so that's 2. What about oxygen? 6. So we have a total of 8 valence electrons to work with, to draw with, okay? So we got H and O, so which one's going to go in the middle? O, because H has to go on the outside, right? So you can orient it however you want it. You could have it up and down, you could have it diagonal, whatever, but just O has to be in the middle. Now, when we draw a molecule, all the elements... Hey, can you guys stop holding hands, please? Thank you. So all of the elements need to be connected, right? So we're going to start by connecting all the elements. So H and O connect, H and O connect. If I draw 2 lines, how many electrons did I use? 4. Yeah, each line is 2. So if we draw 2 lines, we used 4 electrons. We still have 4 to work with. If you take a look, though, what's the problem with this picture so far?
Only used 4.
Yeah, we only used 4, but what else? Yeah, oxygen currently only has 4. How many does oxygen want? 8. So what we have to do is we need to add the remaining 4 to oxygen by drawing these dots to represent these electrons. Okay? And if we do that, oxygen has 2 lines, which is 4. 4 dots, total of 8. So this is where a little bit of new vocab comes out. So these lines, they represent 2 bonding electrons, right? But these dots right here, these are called lone pair electrons. So lone pair electrons. So if we are analyzing oxygen, what we can say is that oxygen has 4 bonding electrons and it has 4 lone pair electrons. And that's pretty much how to draw these structures. We're gonna do one. I'm gonna have you guys try one more on your own. But any questions on drawing it? Hopefully this isn't too bad. Make sure you guys get really good at this. If you need help with it, please let me know so I can help you guys out. Because towards the end of the unit, we're gonna be analyzing these structures, and you're gonna be expected to just draw them and then analyze it properly. Okay. All right. Last one, and then we'll move on to the next topic. I want you guys to do CF4. CF4. Okay, so CH4 and CH3. So let's start with CF4. CF4 is very similar to one that we already did. CF4, carbon has how many valence? 4. How many does fluorine have? 7 times 4, so 28 total. So that means that we're going to have a total of 32 valence electrons. A lot for this molecule. Okay. All right. We're going to put carbon in the middle, same as before, and then it's surrounded by these fluorines. Now, we always start by making our connections. Everybody is connected together. So F connects to C, connects. So all our connections are complete. How many electrons did I use to do those connections? 8. Yeah, 4 lines is 8 electrons. So that means I have 24 left to go. Now, let's take a look at carbon. Is carbon happy? Does it have a complete octet? Yes. There's 4 lines connected to carbon. Carbon is a happy element, so we can move on. If you look at fluorine, though, is fluorine happy? No. How many does it have? It has 2 because it has only 1 line next to it. So how many more does it need? 6. So if we add 6 to this fluorine, now this fluorine is happy, and we've gone down to 18. And you guys can kind of tell by math how it's going to go, right? We add 6 to this fluorine, that's going to get us down to 12. You add 6 to this fluorine, that gets us to 6. And then we get here, and then we've used all our electrons. Okay, so that's CF4. All right, the next one is one that's a little bit trickier. It has a rule that we need that I talked very briefly to you guys about at the beginning of the year. But if you guys take a look right here, you guys see how the H's are separated from one another, right? Whenever you see elements separated like that, what it's basically telling you, it's telling you what the molecule looks like. So if you look on the left side of the molecule, there's going to be a C connected to 3 hydrogens. So on the left side, we're going to put a C, and there are 3 hydrogens that are connected to it. And on the right side, there's going to be an O, and there's going to be 1 hydrogen connected to it. And you guys kind of see what the structure looks like. So keep that in mind. If you remember, great job. If not, that's okay. If you ever see elements separated in the formula, the same element separated, it means it's showing you what the molecule looks like. All right, so let's count our valence electrons, and then we'll see how it goes from there. Carbon has 4. Hydrogen is 1 each, so 3. Oxygen is 6. Hydrogen is 1. We multiply that together, so 8, and then 14 total. Okay, so let's draw our connections. Remember, the elements are separated, so it's telling us what's happening. Carbon is connected to 3 hydrogens, so the hydrogens connect to carbon. That's 6 electrons. Oxygen is connected to hydrogen. That's another 2. And since it's one molecule, the carbon and oxygen have to be connected. That way, everything is connected with at least 1 line. So we've drawn 1, 2, 3, 4, 5 lines. 5 times 2 is 10. So we have 4 valence electrons left over. Now, if you look at hydrogen, they're all happy because they got a line. If you look at carbon, 4 lines, so that's happy. Oxygen is not happy because it has 2 lines. That's 4. Got 4 left. So we draw 4 dots around oxygen, and we're good to go. All right, so that was a little bit of a trickier one, but that's kind of the gist of how it's going. And I know this might seem weird, but as you do more problems and look at more examples, it kind of comes a little bit easier. So If it's a little bit tricky still, don't sweat it. As you are exposed to more of these molecule pictures, it'll be a bit easier.
Like, you can go back and do let's start breathing on. You need that extra practice.
The full? I got half a point less than.
That's still half. Like you see, I'm always locked in.
Who got a 0 out of 10 on the AP pre-calc, Mr. He 1.14 quiz?
That was very
Who's got a
specific.
0
0
out of 10?
I'll go 1.
I got a 1 too. Wait, what? But that's because he got a 0. 1.4. And I got a 2.
I already got like a fucking 4.
On the pre-calc? Yeah.
Good job, Mark. Yo, my
I made the
calculator.
stupidest mistake. The only mistake that I did was the last one. I put the square root. Like, because it was square rooted, so I had to square the answer, and so I got like 11.
I'm actually really sad because I missed all of unit 3 and I got everything right if it was a quadratic equation, but it was a cubic equation. That's exactly what I did. So I literally got everything right, but it was a quadratic.
No, but I put.
Alrighty, guys, let's continue. So we're gonna kind of build off a little bit more on these structures. So I want you guys on your notes to the picture that we just drew. This right here is called a single bond. Okay, so if you have one line connecting two elements together, that's called a single bond. Okay, and again, single bond, it represents two shared electrons. All right. Now, we're gonna be talking about some different bonds now. So let me make some space up here. So we've been drawing molecules with only single bonds so far, but there are other types of bonds as well. The other type of bond we're going to be talking about are called double bonds. Okay. And double bonds are represented by two lines. And if you guys look, if one line is two shared electrons, how many electrons do you think?
4.
Yeah, 4. It's going to be 4 shared electrons. All right, so let's do a quick example just to kind of get you guys familiar with it. So we're going to draw O2, oxygen gas. Oxygen gas has a double bond. I'm going to draw it with you guys just because we're going to do more practice after we talk about all the new content. But let's look at oxygen. If you look at oxygen, oxygen has 6 valence electrons, right? So there's going to be a total of 12 in O2. Okay. So if we're drawing O2, we're going to draw 2 oxygens next to each other. All right. So let's start by connecting them together. I'm going to make one connection. If I make one connection between the oxygens, I've used 2 electrons, right? So that means we have a total of 10. Okay, but if you look, the oxygens are not complete yet, so we're going to have to add some lone pairs, right? So let's start with the one on the left. We're going to draw 1, 2, 3, 4, 5, and 6. If we draw 6, now we have 4. And you guys can kind of see the problem, right? Because if I only have 4 electrons, and if I give the 4 electrons to this oxygen, what's the problem? Yeah, this one is not octet, right? So this one's not happy, but this one is. So this is when we use a double bond. It's when you don't have enough electrons to give everyone an octet with just single. So what happens is this oxygen has to give up these 2, and they have to be shared between the 2 oxygens. And that's called a double bond right there. Okay, so double bond is 2 lines. There are 4 electrons that are shared.
The max is a double bond, right? It can't be
No,
triple.
there's a triple. Okay, so that's a double bond. All right, speaking of which, there is one last type of covalent bond, and if it's single, it's double, and then the next one is triple. And you guys kind of can probably guess what a triple bond is, right? It's going to be 3 lines, which is equal to 6 shared electrons.
Do you do triple at all in honors?
We did triple. Alright, so I'm going to have you guys draw a triple bond. This one I'm going to have you draw on your own because you kind of get the idea now of what they look like. Let's do N2. Okay, take about 2 minutes. See if you could draw N2. Okay, let's start by counting the elements, or the valence electrons, excuse me. Nitrogen has 5 each, so it has a total of 10, right? So if we draw nitrogen, or N2, we're going to draw a line in between them, and I already told you it's triple, so let's draw a triple bond. That is 6 electrons, so that we have 4 left. Now if you look at this nitrogen, there's 3 lines next to it, so it has 6. It wants to get to 8, so we draw 2. We've got 2 left. And then the remaining 2 go right there. So that's going to be your triple bond example. So yeah, theoretically there could be a quadruple, but the problem is, what do electrons do to each other? They repel, right? So if you pack that many, it's not going to, yeah, that's the reason why. If you could create a quadruple bond, you probably win a Nobel Prize, so good luck with that. Hopefully one of you do it, and I'll take all the credit. All right. We'll finish up with doing a couple examples. Oh, actually, before we do a couple examples, let's we're gonna talk real quick about something you need to know. Now, as these bonds, as we go up in these shared electrons, right? So single, double, and triple bonds. Key thing to remember. So let's do single, double, and triple. As you go up in the shared electrons, key thing to keep in mind is that these bond lengths are shorter. Okay, so shorter bond length, which means these bonds are stronger and they're closer to, the elements are closer together. Okay, so just keep that in mind. Triple bond is the strongest type of covalent bond. Single bond is the weakest. Okay, it takes the most energy to break a triple, and it takes the least energy to break a single. Okay, and then a single is going to be a very long bond length, so that means they're further away from one another, whereas triple is going to be the closest together. Okay. And we'll come back to this at the beginning of next class, but just keep that in mind. Single is the weakest, triple is the strongest. Single is the longest, and triple is the shortest. Okay, so short people like me are super strong. That's what it's saying. S tier cope. All right. Let's do a couple examples, and then yeah, we'll be done for today. So I'm gonna have you guys draw a couple molecules, and this is going to be mixed. So there's gonna be a bunch of different types of bonds that we are looking at. First molecule I want you to draw is HF. Second one I want you guys to draw is CO2. And then the third one I want you to draw is CN, God bless you, minus. Okay, so let me give you guys about 5 minutes or so, and then we're going to go over it together, and then we'll be done. Alright guys, let's start going over these. If you're still working, feel free to finish up and just check your answers, but for the sake of time, I'm going to start going over the answers, okay? So HF, pretty easy for this one. H is 1 valence, F is 7, so we got a total of 8 valence electrons. So we're going to do H and F next to each other. We connect them. That's a single, that's 2 electrons, but we got to get to 8, and fluorine needs 6, so we put 6 on fluorine. So that's HF. Probably the easiest one. Alright, moving on to CO2. This one's a bit tricky. C is 4. Oxygen is 6 each, so that's going to be a total of 12. So that means we have a total of 16 to work with. We said carbon always goes in the middle, so we put a carbon in the middle. And then it's going to be surrounded by 2 oxygens. So first thing you want to do is just see if you can make the single bonds. So connect them together. So we're going to draw 2 lines. That's going to get us from 16 to 12. So far, so good? Okay. We need to give everybody an octet. So let's start with the oxygen. Let's go left to right. Oxygen, this needs 6 to get its octet. If I use 6, it goes from 12 to 6. And I'll give the other one 6 as well. That's how we use all the electrons. But the problem, if you look now, is carbon does not have an octet, right? And so carbon needs an octet. How do we do that? We take 2 from the oxygen on this side. We give it a double bond. Now, this oxygen still has an octet, but carbon has 6 because it has 3 lines next to it. And then you can see this oxygen also needs to share. We got CO2 like that. Okay. All right, and then the last one, carbon is 4, nitrogen is 5. The negative sign means that there's 1 more electron, so we're going to add 1 more electron. That'll get us to 10. We're going to start by drawing C and N next to each other. Cn, oop, not that close. Cn. We're going to put a single next to it, and then let's just put more electrons on it. Carbon needs 6 more. That'll get us to 2 left. We give it to nitrogen, but nitrogen now does not have an octet. We're going to move 1 pair to make a double bond, but if we do that, nitrogen is still not happy, and so we got to finish it up by adding a triple bond in between them. Okay, and then for the last thing for this one, you need to put brackets around it and put a minus sign because it's an ion.